All right, let's go ahead and get started. I do want to welcome you to the first installment of Unit 1. This is Properties of Matter. We have successfully studied now the preliminary information for this unit, and that was measurement, the nature of science, and safety. So I hope everything went okay on that first examination, and we're going to continue now with properties of matter. So we're going to start with a question, and the question is, what is matter, right? What do we mean by matter? Well, really the criterion are very simple. Anything that has mass and occupies space is matter. You've probably known that for a long time now. Anything that occupies space and has mass. So let's kind of ask some questions about materials that are familiar to us. It's obvious that the table in front of you is matter because it has mass, clearly, and it occupies space. But what about something like air? Is air matter? Well, does it have mass? Well, I can do an experiment in which I take a bicycle tire and measure the bicycle tire before I put the air in it, and then I can put air in it and measure it again. And what I find is that the bicycle tire with the air weighs more than the bicycle tire without the air. So clearly, air has mass. And the volume, well, that's evident. If I fill a basketball with air, the basketball has some volume, so it has volume as well. So even air, smoke, and water vapor are matter since they have mass and volume, right? Since they have mass and volume. How about light? Say light from an incandescent bulb. Would that be classified as matter? Well, no, because light doesn't have mass. It doesn't occupy space. It's pure energy. So I think we've got a pretty good idea then of what matter is. So let's start now to classify matter and look at different techniques for classification of matter. Let's start with classification through a system that you've, again, known for a long time, and that's solids, liquids, and gases. So I've shown on the left-hand side a diagram of what the particles, if you could see them in a solid, might look like. Solids are very rigid in nature. In other words, the particles don't move around very much. And furthermore, the particles are very ordered. They're in what we call a lattice. Let me write that down. L-A-T-T-I-C-E. That's a T. L-A-T-T-I-C-E. That is the formation of the particles in any kind of a solid, whether it be a gold ring or a rock or piece of granite, whatever the case may be. That's what we're going to see. If you could see the particles, they would line up in a lattice just like that. The bonds, we'll talk a lot about the bonds or the forces that hold those particles together, are quite strong for a solid. Okay? Now, solids have a definite shape and a definite volume, right? You can't change the shape or the volume of a solid. So that's what we call a solid. The second category that we're going to look at is called a liquid. Now, a liquid doesn't have this lattice. The particles are more free, certainly, to move around because the bonds which hold those particles together are not as strong. They're not as rigid. Therefore, we say that liquids take the shape of their container and they have a definite volume. They are not what we call compressible. The particles of a liquid are able to easily slide across each other and are not as rigidly held by strong forces between particles such as they would be in solids. So that's liquids now. Let's look at the last category. We're going to call this one gases. And we're all familiar with gases. We have a whole unit on gases at the end of the year, but gases have neither a definite volume nor a definite shape. They are compressible because there's lots of empty space between the particles that make up the gases. This is called a volumetric flask. Not that you need to know that, but this is called a volumetric flask. This one is called a beaker, by the way. We'll talk about that later. But at any rate, clearly the gas particles take the shape of their container. There's a lot of space between the gas particles as opposed to the liquid particles, and certainly as opposed to the gas particles, right? So what we say then is that the particles of the gas have lots of what we call kinetic energy. I'm going to just abbreviate it. I won't write it out. Kinetic energy means this. It's the energy of motion. All right? The energy of motion. And next year in physics, you're going to learn a lot more about kinetic energy, and you'll learn the formula for kinetic energy. I'll just give you a little preview, though. Kinetic energy is equal to 1/2 the mass times the velocity squared. 1/2 the mass of the particles times their velocity squared. We'll worry about that next year, though. Just wanted to give you a little bit of a heads up for what's coming. So, at any rate, now that's it. Solids, liquids, and gases. That's one way of categorizing matter into solids, liquids, and gases. Now, one last thing before I leave this categorization system, and that is this. I want you to know that these two right here, liquids and gases, are what we call, I'll write it down here, they're what we call fluids. And by fluids, what we mean is that the particles slide past one another. So, for example, if I have a pitcher of water and I pour the water out, the particles slide past each other. The same is true of gas, or I should say smoke, billowing out from a burning building. The particles slide past each other because the forces that hold them together are not very strong. So solids are not fluids, but liquids and gases are fluids. So that's it. That's one way of classifying matter. All right? I hope you got that. Let's take a look at another way of classifying matter, and that's this way. We can take all the matter in the universe and we can classify it into pure substances and mixtures. All right? Pure substances and mixtures. And we can further classify pure substances into elements. Gosh, we're going to spend a lot of time this year talking about elements, and also compounds, right? So elements and compounds are pure substances, and mixtures can be classified into homogeneous mixtures and heterogeneous mixtures. Another name for homogeneous mixtures is this: solution. I'll try to write this clearly. Solutions. A homogeneous mixture is a solution. So homogeneous mixtures and solutions is the same thing. And of course, heterogeneous mixture. So matter can be classified as either a pure substance or a mixture, and then pure substances can be classified as elements and compounds, while mixtures can be classified as homogeneous or solutions and heterogeneous mixtures. All right, so that's one way, or second way then, of classifying matter. So let's concentrate for a while then on mixtures, right? Mixtures are exactly what the name implies. They are mixtures of different types of pure substances. For example, if you mix salt and water, you get a mixture. So if I take a glass and I put water into the glass, so here's the water, and I put salt into the water, I have a mixture, right? I have a mixture. So if you mix oxygen, nitrogen, argon, and a few other gases, you get a mixture called air. So the air in this room right now is a mixture. Stainless steel is a mixture of metals. So we see mixtures all around us. Now, mixtures can be separated by physical processes. Remember, mixtures by physical processes. For example, a saltwater solution, like the one we just created here, can be separated into salt, which is a pure substance. The salt, by the way, is the formula for it is NaCl. That's salt. And water, which is also a pure substance. So water is H2O. And so we can separate those two pure substances by evaporating the water so that only the salt remains. Now, pure substances, on the other hand, can't be separated by physical means, and we'll describe those physical means a little bit later. So let's say we've got a mixture of water and alcohol. All right, let's say we've got a mixture of water and alcohol. All right, they can be separated by a process that's known as distillation. I want to describe the distillation process for you. Distillation is a process which allows me to separate two liquids with different boiling points, different boiling temperatures. That's critical. So alcohol has a lower temperature, boiling temperature, than does water, right? And will vaporize more quickly when the mixture is heated. Thus, I can separate the alcohol from the water. So let me show you how this distillation apparatus works then. I have a distillation flask, that's this part of the apparatus right here, that has within it two different liquids, alcohol and water. By the way, the formula for water, again, is H2O. We're going to call, and just write this down for now, it's ETOH. We're going to call that ethanol. I'll explain that later, probably much later, okay? So at any rate, I've got a mixture of these two liquids, water and ethanol, this alcohol, And what I'm going to do is I'm going to separate them. How am I going to do that? Well, this is the distillation flask right here. Below the flask, I have a Bunsen burner to supply heat. Now, I have a thermometer above the distillation flask. The temperature of boiling for water is 100 degrees Celsius. I'm going to say, and by the way, I'm making this up, so please don't look this up, but I'm just going to say it's 83 degrees. I know it's lower than 100 degrees. I just don't know how much lower, so I just made that number up. It doesn't really matter, because what I want to show you then is this. The idea is that I'm going to use the Bunsen burner and the thermometer to help me calibrate or help me to determine a temperature above the 83, above the boiling temperature of the ethanol, but below the 100. What's going to happen? What's going to happen is that the ethanol will begin to vaporize. It'll hit that thermometer right there at that junction right there, and it will begin to vaporize, but it'll fall this way. Now the vaporized, this is clever, the vaporized ethanol is this, and then is then going to go through a cold tube called a condensing tube. Now the way the tube works is it's a tube within a tube, really. This is a water inlet for cold water coming from the faucet, from the sink, and this is a water outlet going back into the sink. So the outside is cooled, causing vapor inside in the inner part of the tube to condense, right? It forms a liquid again, and it falls because it can't go back, so it's going to fall down into this test tube right here. So what's going to happen is that eventually the alcohol water mixture then is going to be separated. So we're talking about a physical separation technique that separates two liquids based on their differing boiling points, okay? So that's it. That's our first physical separation. So remember again, mixtures can be separated by physical means. Pure substances cannot be separated by physical means. Those require something called chemical means, and I'll show you those in a moment. All right, so here we go. So let's keep focusing on mixtures. There are two types of mixtures. There are homogeneous mixtures and there are heterogeneous mixtures. Homogeneous and heterogeneous mixtures. Mixtures can be separated by physical means. We've said that already, such as filtration. I'll show you a filtration device using something called a Buckner funnel. Distillation. So, by the way, filtration is based on particle size. So if I have big particles and little particles, and the little particles can make it through a filter and the big particles can't, that's a physical separation. Distillation we've already looked at, and evaporation. Pure substances cannot be separated via this means, all right, via this means. So now, homogeneous mixtures are the same throughout. For example, if I take a small amount of sugar and I dissolve it into water, the result is a homogeneous mixture, otherwise known as a solution. Now, the sugar is evenly distributed throughout the water. So if I have a situation where I have an even distribution, of sugar and water, we're going to call that a solution or a homogeneous mixture. A solution or a homogeneous mixture. So here we go. So here I've got sugar and water, and I've got a sugar and water, and I stir it very well. Maybe even heat up the water a little bit. You'll find later on that that increases the solubility or the amount of sugar that can be held in the water. And the sugar-water solution is what's going to result, right? So another example of homogeneous mixture or a solution is air. Now, air is a homogeneous mixture since the gases that make it up are roughly equally distributed in the container which holds the air. Heterogeneous mixtures are not the same throughout. For example, if I mix a large amount of salt in a glass of water, some of the salt will form a layer on the bottom of the glass. So the mixture of the salt and water is not constant throughout. That would be a heterogeneous mixture. So the difference between a homogeneous mixture and a heterogeneous mixture, if I'm talking about a salt-water solution, is for a homogeneous mixture, I'm going to stir it very well. There's no layer on the bottom. The salt's completely dissolved. For a heterogeneous mixture, there's a layer of salt on the bottom. That is not a homogeneous mixture. That will be a heterogeneous mixture. I'll see you on the next one. Thanks. Bye.